Welcome, students. This is your instructor, Sandra Hindo. We are officially on Lecture 5 of Lean Six Sigma Yellow Belt. If you are following along in your official Lean Six Sigma Yellow Belt PDF or the official slide deck, please turn to slide number 122. Again, in your official slide deck and PDF, we are starting on slide number 122. Let's get started. Process capability analysis case study. Software support. Software development and support. Background. A software project manager is responsible for leading 15 developers, 11 experienced, and 4 recently hired. Product delivery. Providing support service to users of the existing product. Development schedule for the new product assumes product service support will require 40 hours per week until the product is released. What are the constraints? Development team to provide support at any point of time. Daily effort to support service requests must be within the limits assumed by the plan in order to keep the development schedule on time. Capability. Capability indices include CPK, CPU, and CPL. Every indice or index taps into whether or not your process is capable. Your process can be extremely capable, moderately capable, or not capable at all. Measures of potential process capability calculated with data from the subgroups in your study. They measure the distance between the process average and the specification limits compared to the process spread. Let's look at CPL with the highlighter. CPL is right here. CPL measures how close the process mean This is the mean, y'all. Y'all see that? And if you want to see what the mean is or the average, it's right here. So mean, also known as average, it's 40. Where do you find it? Right here. It's 40, and this is the upper specification limit. So let's look at the capability index. The first one, CPL. CPL measures how close the process mean is running to the lower specification limit. And then you have CPU. CPU is right here. CPU at 1.19. And you can tell CPL, there's nothing on there, so they couldn't calculate it. But CPU is 1.19. And the reason they couldn't calculate CPL, because in this example, there wasn't a lower specification limit. So that means the less the better, right? But for the CPU, it's 1.19. So what does CPU do? CPU measures how close the process mean is running into the upper specification limit. And y'all know it's not only is this average running into the upper specification limit, it has surpassed it. This is not good. And then you have CPK right here. CPK equals 1.19. CPK equals the lesser of CPU and CPL. If CPK, CPU, and CPL are equal, the process is centered at the exact midpoint of the specification limits. Compare your values to benchmarks to determine whether to improve your process. Many industries use benchmark values of 1.33. So you can tell these are not 1.33, and that's evident because even if you visually look at it, you can see all of these data points are surpassing USL, which is not good. So you have your process capability improvement goal. And at this moment in time, are we meeting it? Well, it's very easy. Always look at the output. Once you punch in some numbers into the Minitab statistical software, what do you have to do? Look at the output. If you see any data points that are above or below, if they're below the lower limit or they're above the USL, no good. You gotta improve the process, as simple as that. Current capabilities at 1.19, not good. Expected long-term capability, 0.99. Rationale for goals, 0.33 mm revenue increase. And not to get too much into the math, but in this situation, the CPK equals 0.51. And then when the CPL is less than the CPU, the process is not centered. It is more likely to produce defective units that violate the lower specification limits. When CPL is greater than CPU, the process is not centered. A disadvantage of the CPK index is that it only represents one side of the process curve and tells you nothing about the other extreme. For example, the two graphs below display processes with identical CPK values. However, one violates both specification limits and the other only violates the lower specification limits. To avoid mistakes, consider all of the capability indexes along with a graphical summary to draw meaningful conclusions. Process stable, but 6.25% of the results have fallen outside the specification limits. So let's take a very careful look at this. Y'all see this in yellow? These are all data points. And because these data points are above and beyond the upper specification limit number, which is 50, it's not good. And if you want to know what percentage of the results have fallen outside of the specification limits, you need to look at these numbers. Let me show you very carefully. You got to always look at what? The parts per million total. So y'all see this, the ppm total. You got to move it, move it, move it. Decimals right here. So it will be the 6.25% fall outside the specification limit. Ideally, I would want to see a very, very tight process where we don't even get anywhere close to the USL. So we have a tighter data points, which means more consistency, more predictability, and more repeatability. And I always tell students, don't get so bogged down in trying to understand the inner workings and how all of these complicated mathematical formulas are drawn. Your job is to look at the visual. And ideally, you want your data to be nowhere close to any specification limit. Process capability analysis case study. This time we're looking at the telecom sales. ITES, telecom process voice. Process sigma level is equals 0.52. And the lower specification limit in this example is 15. The mean is 20.75. And we're looking at 32 samples. And how much is the standard deviation? Well, it's spreading plus or minus 9 points. So plus or minus 9 points. And what does a standard deviation means? It means the spread. Spread to the left, spread to the right. And just by looking at this, I don't like what I'm seeing at all, okay? Because in this one, you know how the other one, there was an upper specification limit? Well, this one doesn't have an upper specification limit. It just has a lower specification limit. You can tell it's like smack dab at 15, right? And I see all of these data points that are below the LSL, which is not good. So I look at this and I say, hey, we definitely need a Lean Six Sigma practitioner in here. And we need to make the improvement. So an estimate of the variation of your process output. Minitab uses several types of standard deviation to capture different patterns of variation in a process. Within subgroup standard deviation, S within, represents the variation within your subgroups. For example, the variation in output from one worker, one shift, in one batch. Between subgroup standard deviation, SB between represents the variation between subgroups. For example, the variation between the output of different shifts or operators. Between/within standard deviation is a single value that accounts for the variation between subgroups and within subgroups. Overall standard deviation, also known as S overall, represents the variation of the entire process output ignoring subgroups. It is calculated by combining data from all subgroups and treating them as a single sample. This is the variation the customer experiences because the distinction between subgroups disappears when the customer receives the process output. That was a mouthful, and it's all going to be in your PowerPoint slide deck notes. Keep it simple, y'all. Keep it very, very simple. What you want to do for your Lean Six Sigma project is that you're looking at these telecom sales equals, from September 2024. You're looking at it. This is what you're going to do in your report. This is what the process looked like before the improvement plan. And then you get your team together. You train your employees. You get the job done, right? You make everyone follow the same steps, follow the same procedures within the same time limit. You do the improvement, make sure everyone's following it, and then you do your post-improvement plan numbers. And what I always tell students is this one should be your before improvement plan. Show them the picture, and right next to it, side by side, you're going to show them your post-improvement plan numbers. And what I want to see in every single Lean Six Sigma report, if you were a successful practitioner, not all practitioners are successful, right? Because I always say it's easier said than done to get people to change the way to do things, right? You got to get leadership support. You got to get everyone on board. But if you do it right next to this bad graph, you're going to see a post-improvement graph. And in that, ideally, you're going to see data that looks more like this. Well, let me just show you. You're going to see data that's much more tight, much more in the middle of the ideal target level. Current process capability is 100% minus the 30.29% equals 69.71%. Whoa. Do you want a current process capability at only 70%? Absolutely not. Improvement is needed. And so if you're sitting there and saying how you calculated, you take the 100% minus the 30.29%, and this is not good at all. Number of agents was 32. Minimum sales target, 15 sales per agent per day. The mean sales achieved, 20.75 sales agent per day. What's the financial impact of this? Not good at all. Now let's take a good look at the CPK. There's this capability index is not available, the CPM. We see all these numbers falling outside of the LSL. This is the CPK is nowhere close to where it should be. This process as it stands is not capable, not highly stable. So there's a lack of inconsistency. Quantifying the gap or opportunity. Current process capability is almost close to 70%. With 30% of sales not reaching the target, the potential loss could be $150,000 per month. And so as a Lean Six Sigma practitioner, when you're working on your project, you're going to have a nice section with a heading called COPQ. This is where you talk about the people that are purchasing the raw materials, the people in the quality department, your HR for overtime, and you need to calculate for every project the COPQ, which, as you can see here, it's the cost of not fixing the errors, the cost of not removing the inefficiencies, not getting, keeping process steps that you don't have to keep. And maybe you have a few employees repeating the same steps, and there's so much waste happening, right? And you come in, you have to map those processes to figure out what's causing 30% of sales not reaching the target. And make sure you do a really great job in your report of connecting the dots between what's the cost of all of these errors, mistakes, and the potential loss or the excessive amount of money that your department is spending that you don't have to be spending if you change your process. Really, really powerful. And when we get to the black belt, I'm going to show you that connecting the dots in the section titled COPQ, Cost of Poor Quality, is a must. Because when you have a very solid COPQ section in your report, what you are doing as a practitioner is justifying why you're spending the next 1-2 months training your employees and making those improvements. And if you can end it with a before and after graph, say, look how far the spread is. You have all this data outside of the lower specification line. And process capability, look at it. It's only at 70%, and we're losing this much money. But look, I came in as a practitioner, and look at my after graph, and look how everything got tighter. That means you succeeded as a practitioner. And you're going to get there. We will learn how to do this in Minitab. Process capability analysis for software development. IT software development projects. PPK, PPU, and PPL. These three indices are measures of overall process capability calculated with overall process standard deviation. They measure the distance between the process average and the specification limits compared to the process spread. PPL measures how close the process mean is running to the lower specification limit. PPU measures how close the process mean is running to the upper specification limit. PPK equals the lesser of PPU and PPL. If PPK, PPU, and PPL are equal, the process is centered at the exact midpoint of the specification limits. Compare your values to benchmarks to determine whether to improve your processes. Many industries use the benchmark values of 1.33. Let's go look at this and see what the numbers are. Upper specification limit, 20. I always tell students, don't complicate this. You see all these data points above and beyond the USL. Not good. The mean is almost 15. Sample size is 27. Standard deviation is 5. And honestly, I'm just looking at this right now, and the PPK, it's 0.22. And what did we say the benchmark values are for high process capability is 1.33. So when you're seeing numbers, when you're seeing a PPK at only 0.22 and the benchmark value to be a highly capable process is at 1.33, you're nowhere where you're supposed to be. You should also know a disadvantage of the PPK index is that it only represents one side of the process curves and tells you nothing about the other extreme. For example, the graphs below displays processes with identical PPK values. However, one violates both specification limits and the other one violates the lower specification limit. To avoid mistakes, do consider all indices along with a graphical summary to draw meaningful conclusions. And looking at even the CPK, it's nowhere close to the 1.33 either. So we are looking at all of them, and visually this is not looking good with all these data points here. So in this example, all these data points right here, above and beyond the USL, 74% of the projects will have defects within the target level of 20 defects per project. Not good at all. Parts per million, 255,411 defects per 1 million opportunities. Y'all, is this anywhere close to being Six Sigma? No, because if it's close to Six Sigma, what we would be seeing is only 3.4 defects per million opportunities. So how in the world can you compare 3.4 to 255,000? We are now going to look at measurement system analysis, graph R&R. What is measurement system analysis? Methods to evaluate your measurement system and determine whether you can trust your data. MSA helps determine how much of the overall process variation is due to measurement system variation. Measurement systems can include your data collection procedures, gauges, and other test equipment. Evaluation of your measurement system should be done prior to control charting, capability analysis, or any another analysis to prove that your measurement system is accurate and precise and your data is trustworthy. Sometimes different measuring devices and operators can assess the same part or sample and generate different results. Many different situations, such as machine calibration problems or operators follow different procedures, may cause these differences. The more error in the measurements, the more likely you are to make an error in your decision based on those measurements. MSA tools help you evaluate accuracy and precision in your measurement systems. MSA tools include Gauge R&R study, Gauge Run chart, Gauge linearity and bias study, Type 1 gauge study, attribute agreement analysis, and attribute gauge study. We're going to be looking at MSA very carefully, first with the Gauge R&R. Reasons for measurement. If we can't express something in the forms of numbers, we don't know much about it. If we don't know much about it, we can't control it. If we can't control it, we're at the mercy of chance. So you got the measure, process, product, knowledge, understanding, analysis, and improvement. Here it goes. If we can't express something in the form of numbers, we don't know much about it. If we don't know much about it, we can't control it. If we can't control it, we're at the mercy of chance. Whatever you don't measure can be very dangerous. A process produces two outputs. 1, goods and services. 2, measurements to manage and improve processes. So you have inputs that go into a process, and then the process creates outputs. Evaluating a process. You have inputs go into a process, and the process produces outputs. Parts example. Any information we gather about the process behavior must first pass through a sensory system. Inputs, processes, outputs. We need to do observations of the outputs, measurements, and collect data. A measurement system not only includes the instrument used for the measurement, but may also include sample preparation or user/instrument setup, which is required for a measurement. The measurement as a process. In other words, we must submit the output from the first process to a second process. Measurement process, outputs, observations, measurements, and data. And I always tell students that when you're going to go ahead and you're going to collect your data, it might already be available to you. It might not be. You're going to have to collect the data yourself or have a team member do it, but you got to be careful. The person that's collecting the data, it's going to be their observations, their measurements. Are they trained? Are they measuring things correctly and consistently? So you might think that you're dealing with true data, and you may not be. So definitely understand who's collecting the data and are they trained or not. Because this could all result in measurement error, which then doesn't, that somewhat de-invalidates how true your data is, right? So we want to make sure the measurements are accurate. 3 questions about measurements and measurement systems. Is it valid? Am I measuring what my customer thinks is critical to quality, CTQ? Yes or no? If yes, what must I do to show I'm measuring a CTQ? Is it reliable? Is the measurement system accurate, stable, repeatable, reproducible, and linear? Yes or no? What must I do to show measurement system as all these properties? Do specifications exist? What is the order of magnitude of my measurement? What are the specification limits for the measurement? Yes, no. If yes, are the specifications valid? What must I do to show their validity? Answering these questions is at the heart of the measure phase. Bad measurement systems can cause us to scrape good products and ship bad ones. This is a good gauge, true value for the CTQ, and this is a poor gauge. What is a gauge? A gauge is any instrument or device used for obtaining measurements. Examples include a ruler. A ruler measures the length of an object. A caliper, also used to measure length, but generally much more precisely than a ruler. And then you have another instrument, a depth gauge. That measures the depth of holes, cavities, or other component features. Then you have a snap gauge. That measures diameter or thickness. And then you also have a go/no-go gauge. This measures a manufactured items and determines whether it meets dimensional tolerances. It is an attribute gauge because a part is rated as good or bad, pass or fail. It is commonly used in production because measurements can be made very quickly. Selecting the appropriate gauge will depend on the application, what you want to measure, and how you want to use the data. If you simply want to separate good parts from bad ones, then fixed size go/no-go gauges may provide all the information necessary. If you want more information on how good or bad a part is, for example, to assess capability, use gauges with numeric readouts. Next, we have gauge repeatability and reproducibility study, gauge R&R study. So what is a gauge R&R study? It is a measurement system analysis method which evaluates your measurement system precisely and estimates the combined measurement system repeatability and reproducibility. So R&R stands for what? Repeatability and reproducibility. A gauge R&R study helps you answer whether your measurement system variability is small compared within the process capability, how much variability in the measurement system is caused by the difference between operators, and whether your measurement system is capable of discriminating between different parts. That was a mouthful, and it's all in your notes. What I'm going to tell you is gauge and R can simply be defined as followed. Repeatability: can the same appraiser get the same results, consistent results over and over again? And then reproducibility is, can different appraisers draw the same numbers, measure the same numbers over and over again, right? So in an example of, let's say, the barista who works at Starbucks, can the same barista make that same quality drink over and over again at around 2 minutes? And then reproducibility is, can a multitude of baristas make that drink over and over again within 2 minutes, right? That's just an example, like a little symbolic example. Part is rejected even though it is good because it falls outside of the specification limits. That's scrap. That's a waste of money. Part is accepted even though it is bad. A poor gauge can impact the cost of quality. And this is honestly just a fancy way of saying that make sure your measurement system itself is calibrated. If there are human appraisers involved, make sure they're trained and all of the appraisers are consistently measuring the output correctly. If not, guess what? Your measurements are only as good as the appraisers, only as good as the instruments used, or and those instruments are as good as if they're calibrated, right? There's a multitude of things involved, and this whole point here is making sure whatever measurement tool you use, especially if it involves human appraisers, that they are trained. So here it goes. Possible sources of variation. It could be actual process variation, but it could be measurement variation. It could be long-term process variation, short-term process variation, within sample variation, but then there could be a variation within the measurement itself. The variation is due to the gauge. Variation is due to the operator. Reproducibility, stability, time dependent, linearity, value dependent. Is it accurate? Is it precise, your measurement system? If not, we got problems. That means we're going to have a hard time with repeatability, producing the same data points over and over when measuring the same item. So honestly, you only want pure error. And you do not want a replica of errors because of measurement variation, whether that's due to the instrument itself or is due to the appraiser, also known as the operator. So we definitely want pure error, actual process variation, and we don't want measurement variation. Repeatability is just the variation observed when the same operator instrument measures the same part, also called replicate or pure error. This is the fundamental error by which all conclusions regarding the interpretation of data are made. Only through a sound estimate of replicate error can other factors which may influence the data be judged. Replication is an important part of any instrument. Reproducibility is the variation observed when a different operator/instrument measures the same part. So that's where you get the word gauge R&R study. It helps assess the repeatability and reproducibility in measurement systems. To address actual process variability, the variation due to the measurement system must first be identified and separated from the process variations. A major assumption is that the measurement system and the product response are independent. Let's look at the relationship between the observed variation, the product variation, and the measurement variation. So here it goes. Product variability, which is the actual variation, plus the measurement variability, that includes the total variability, observed variability. SP stands for standard deviation of the real capability. ST stands for the standard deviation of the observed capability. And SM is the standard deviation of the measurement system. Gauge R&R examines this measurement system variation. And what you're going to learn about when you get to the black belt course is that you literally just look at a gauge R&R table for interpretation. And depending on what your final gauge R&R number, you can determine whether your system is highly reliable and reproducible, somewhat reliable and reproducible, or an epic fail, not at all. You're going to learn about the interpretations soon. Let's look at the fundamentals of metrology. How do we know our data is good? Metrology, the science of measurement, provides a set of principles for development and management of measurement systems. The major issues in metrology and measurement assurance include the following: specificity, measurement types and scales, accuracy/bias, overall precision, repeatability, reproducibility, linearity, stability. Accuracy is the ability to obtain the true value of a characteristics. We usually speak of accuracy in terms of bias, or the difference between the average value of repeated measurements and true values. Thus, bias is generally expressed as true value minus what is measured. The difference is the bias, right? For some physical characteristics, there are known standards maintained by the National Institute of Standards and Technology. However, for most service and administrative processes, there are no such known truths. In practice, one of the most important means of maintaining accuracy is the use of operational definitions. Accuracy is the ability to obtain the true value of a characteristic. Spoken in terms of bias, or the difference between the average value of repeated measurements and the true value. I often tell students when it comes to bias, it's the true value minus the observed value, right? Or in other words, the true value minus the number you come up with when you measured it yourself, right? Because there is measurement error. This is how bias is generally expressed as, where F is known as a true value. And what is this? This is the observed value. The observed value takes into account two factors: the measurement system itself, the tool used itself, and whoever the observer or the appraiser is, and the mistakes and errors they can make when they're measuring it. So I tell my students whatever the observed value is minus the true value. In practice, one of the most important means of maintaining accuracy is the use of operational definitions. Accuracy is the ability to meet the true value on the average. Measurement assurance, precision. Precision is the ability to get similar answers in repeated trials. Precision is the combination of repeatability and reproducibility. Repeatability is the ability of a single person to get the same measurement through repeated trials with the same instrument on the same sample. So it's that same barista getting the same measure when measuring the same item over and over again. Reproducibility, on the other hand, is the ability to get the same answer for a standard sample with different people doing the measurement. So different baristas making that same exact standard, grande hot latte, getting the same numbers among many, many different baristas over Monday, Tuesday, Wednesday, Thursday, month after month. That's reproducibility. Overall precision is expressed as the standard deviation of the measurement. This is the formula for precision. Don't get bogged down with this formula. Precision is the scatter of a series of measurements. We can separate overall scatter into its principal sources. Gauge repeatability, that's within the same appraiser, correct? Gauge repeatability is the variations in measurements obtained when one operator, one barista, uses the same gauge or measurement process for measuring the identical characteristics of the same parts or items. So one operating, having consistent data, one operator, one appraiser, that's repeatability. Possible causes of poor repeatability. Well, let's look at them. Could be a problem with the equipment itself. Gauge instrument needs maintenance. The gauge needs to be more rigid. The clamping of part needs improvements, for example, manufacturing example. And another possible cause of poor repeatability is the people themselves. The appraisers, the operators, y'all know they get tired. Well, I'm just using my tool. I think it says 1.5 centimeter, and you're eyeballing it and you're kind of tired, or, you think you saw a 1.4, but you really saw a 1.25. It happens, right? People, environmental conditions, lighting, noise, and physical conditions such as eyesight. Or maybe you're just tired and you hope nobody notices, right? I've often been told by manufacturing folks, a car that comes out on a Friday, you got to be careful because people are tired and they make more mistakes. They're ready to go home. You know, that's just an example. There's real human errors, human tiredness, whatever you want to involve. If any type of process involves a human, just be aware of that. I think just being aware and training your employees on that to look out for that is very helpful. Gauge reproducibility. Gauge reproducibility is the variation, the average of measurements made by different operators, different appraisers, using the same gauge or measurement process when measuring identical characteristics of the same parts or items. And then you have reproducibility, mean of the measurements of operator A, mean of the measurements of operator B. Possible causes of poor reproducibility include measurement procedure is unclear, operator, developer, reviewer is not properly trained in using and reading the gauge, operational definitions are not established for transactional applications. So now you just understand the total gist. Could be an issue with the tool itself. It could be an issue with the operator or the appraiser. Gauge characteristics. The difference between the true value of what you're measuring and the observed average is known as what? Accuracy. Precision is all about repeatability. Then you got stability. Is the mean averages stable over time? And you see like the average is right here, then boom, it shoots up to here. So it measures stability. And then reproducibility, that's among different appraisers. And if operator A is measuring the same exact item, and operator A is getting an average mean right here, but operator B is getting average mean right here, it's not good. That means it lacks producibility. And then you have linearity, which looks at both accuracy, which is the small part, and the difference between a small part and the observed average, which is the low end, and then you have accuracy again on the high end, the big part, and how far away it's from the observed average. So what does linearity measure? Accuracy. Honestly, you want everything to be high in accuracy, repeatability, stability, reproducibility, and linearity. A Six Sigma Gauge R&R study addresses only repeatability and reproducibility. Gauge R&R methods. How to use Gauge R&R for continuous data. You have a short method, quick method with 2 operators and 5 samples. Reproducibility cannot be separated from repeatability. It might be useful to verify a suspected good gauge or if the parts are very limited. Otherwise, this method is not recommended. And then you have the ANOVA method, analysis of variance. This one is recommended. Typically, there's 2 operators measuring 10 parts twice. It allows for separation of reproducibility and repeatability components, easily quantified using Minitab, provides graphical output in addition to values. R&R studies must be performed over the range of expected process outputs. Gauge R&R short method. To use the Gauge R&R short method, operators measure the same parts once. They calculate range of measurements for each sample. They determine measurement error using the average range. They determine measurement error as a percent of tolerance. And tolerance equals acceptable range, which is USL minus LSL. And you use the following to determine if a measurement system is accurate. This is for all Gauge R&R studies. So if your final Gauge and R&R number, after you inserted all of your data points, right? If your Gauge R&R final number is between 0 and 8%, that's an acceptable. That means your process is high in both repeatability and reproducibility. If it's anywhere, if your Gauge R&R final number is between 9 and 30%, that means you have caution. And if your Gauge R&R final number is greater than 30%, it is not adequate. That means you have the same appraiser producing different data numbers every time they measure the same object, but you also have reproducibility issue. Different appraisers are coming up with different numbers when measuring the same exact object. Not good at all. So honestly, when you get to the black belt course, you're going to see like with the gauge R&R, you're just looking at the final number, y'all. And if it's this number percentage, it's acceptable. If it's this, it's caution. If it's this number, it's not adequate. So like literally you follow a table and you determine how accurate it is. Unacceptable measurement systems. What do we need to fix it? Short run method does not give the information we need to answer this question. You use the ANOVA method to determine where we focus our improvement efforts. So we both have high repeatability and reproducibility. Here's a gauge R&R example, okay? Have reviewer 1 measure all documents once in random order. Ensure the reviewers cannot see any of the other measurements. Have reviewer 2 measure all documents once in random order. Continue until all reviewers have measured the documents once. Repeat these steps for the required number of trials. Enter the data into Minitab and columns as shown. Okay, so you're going to see this in the gauge R&R when you pull out your Minitab examples. But here it goes. George, 0.6, George again, 1, George, 1, George, 8.5, George. And then you have Sumaya, 0.55, 0.55, 1.05, and so on. I'm seeing some variation. Just by looking at these numbers between the two reviewers, I'm seeing variation. The customer says our specifications are USL 1.5 and lower specification limit is 0.5. So far, is there anything that's below 0.5 just by looking at the raw data? Well, this one is 0.45. Not bad, but I would have to look at the other numbers, so we're not going to pull that out right now. We're going to just look at through these slides. So, if you're in Minitab to analyze, you're going to open up Stats, Quality Tools, Gauge R&R Studies. You do have this example available to you in the Minitab files. And you can do the same exact steps on your own. But because this is the yellow belt, we're not focused on doing the statistical test until you get to the black belt level. Parts number is the R&R doc. The operators is the reviewer. The measurement data is the defect density. The method of analysis is ANOVA. The study variation is around, what is that, a 5 or a 6? I think it's 5.15. The upper spec, lower spec is 1, and the alpha to remove interaction term is 0.25. Then you click twice to get the results. And you have your graphical analyses here. You have the ANOVA table variance components here, and you have the percentage contribution table, and you have the discrimination index. ANOVA, variance components assess the amount of variation in response due to random factors. Random factors have levels that are selected at random, whereas fixed factors have levels that are controlled by the experimenter. For example, you conduct a study on the effects of 2 levels of pressure or output measured by randomly chosen operators. Pressure is fixed and operators random. The various components output lists the estimated variance for the operator and the error term. Gauge R&R is variance components assess the amount of variations contributed by each source of the measurement error. plus the contribution of part-to-part variability. The sum of the individual variance components equals the total variation. Sources of measurement error are repeatability, the variability from repeated measures on the same part by the same operator, and then reproducibility, the variability when the same part is measured by different operators. Ideally, differences between parts should account for most of the variability, and variability from repeatability and reproducibility should be very small. In gauge R&R, the amount of variation caused by the measurement system and by the differences between parts. Minitab also calculates the percent study variation, so you can compare the contribution of each component to the total variation. By default, the study variation for each component is 6 times its standard deviation, but you can change the multiplier. AIAG recommends the use of 6 in gauge R&R studies because 6 is the number of standard deviations needed to capture 99.73% of the variation from a source. Ideally, differences between parts should account for most of the variability, and variability from repeatability and reproducibility should be very small. So, I'm not liking this. I'm not liking this at all. This might be too small for you guys to see, or at least on my screen, and I see all of these dots below the lower specification limit and the upper specification limit. And bear in mind what you saw in the output, that was just for like the first few. You didn't get to see all of the appraisers. You will when you look at your Minitab output files. But I really do not like this. There's too many numbers that are below. You guys see the little red line on my screen is very, very small because I'm also looking at my notes, but it's whoa. You see all these data points below the lower specification limit? Not good, y'all. See all these dots? Y'all see them? The dots above the upper spec? Not good, y'all. Not good. And I always tell my students, don't stress yourself out too much. Total gauge R&R. You know how we said you need to have a certain percentage for your repeatability and reproducibility gauge R&R study to be considered good? What did we say? I think we said greater than, I have to go back and look at my notes, but just from memory, didn't we say that 30% or greater, it's unacceptable? And look, y'all, below 30% it was you proceed with Gaussian. So we're not at 30% or greater, but we're close to it. So this is what you do. You go to total gauge R&R and you look at the final percentage. And remember what we learned, anything that's greater than 30%, it's unacceptable. So you know what this tells me? You produce your output that looks like this, and you look at this final number and you go back to your slide just for, accuracy and reassurance that you interpret it correctly, and you say it's either acceptable, somewhat acceptable, or proceed with caution, like the middle number. And then 30% or higher is not acceptable. And because this is not at 30%, it's at 26.23%, we're going to say, according to the table, we proceed with caution. And so there's so much more improvements that can be made to both the measurement tool and the observer/appraisers. And that's what you write down in your Lean Six Sigma report. Let us start with the graphs. How much variation is coming from the documents? Control limits for the measurement system. Because there's all of these dots, there's a lot of variation. What's another word for variation? A lot of standard deviation happening. Not good. How much difference does each reviewer see between the first and second reading? Doesn't look that good. What percentage of the total variation is coming from the gauge, the tool? Is repeatability or reproducibility the issue? How do the average readings for each reviewer compare? Based on this graph, it doesn't really look that bad. I mean, just visually. It's not looking that bad. I think they're pretty close to each other. Maybe not that bad. So they did say proceed with caution, right, based on the number, but it's somewhat different. But based on the visual, it really doesn't look that bad. How do the distribution of the readings for each reviewer compare? How much variation do we see in the readings for the same document? It's pretty, I mean, it's not 100% lining up, but it doesn't look that bad visually. Review the graphs to access the variation and to check for data entry errors. And so I'm looking at these visuals, I'm eyeballing it, they're pretty small, but this doesn't really look that bad. And I think with a 0.26, it does tell us to proceed with caution. It's not totally unacceptable because you're not at the greater than 30%. But if I was just to directly follow the table and not look at these visuals, I'm going to say that we need to proceed with caution based on what the gauge R&R table tells us that we should do. Recap. We went over the Six Sigma statistical definition, calculating sigma values. We looked at measure phase deliverables, process capability study, measure phase tools process capability, measure phase tools gauge R&R, measurement phase tools gauge R&R methods. We've officially reached the end of the course, Lean Six Sigma Yellow Belt. In this course, you are not required to do anything with the Minitab statistical analyses. This is truly starts getting required when you reach the black belt level. So when you move on to the green belt and when you move on to the black belt and even the green belt, I'm going to say at the very, very end. But it's a black belt where you start playing around with Minitab statistical analyses. At the yellow belts, remember there was a white belt, it was elementary. Then it gets a little bit more advanced in the yellow belt, but we're still on theory. Green belt, we're still on theory, but we start introducing a little bit of Minitab. But when you get to the black belt, you're going to get a lot of it. We went over some very complex formulas. Let me reassure you, it's just as good to understand the general theme as a Lean Six Sigma black belt project. I don't want you to get bogged down and say, well, I really don't understand what gauge R&R is. Keep it very, very simple for yourself, y'all. All it is that make sure your instrument is calibrated before you use it, whether it's a ruler, whether it's a gauge. Make sure it's calibrated. And then whoever your appraiser and observer it is, make sure they go through training and they're alert when they are collecting the measurements. Obviously, you're not going to be, with any human observer, you're not going to have 100% accuracy. There is going to be some variation. And it's all up to us to look at the gauge R&R and say how much variation are we going to allow. The visuals say a lot, but you also have to look at your gauge R&R table and just remember those three numbers that you saw in one of the slides to determine, yes, repeatability plus reproducibility as a whole is either good, proceed with caution, or not acceptable. So this brings us to the end of the course, Lean Six Sigma Yellow Belt. I hope you enjoyed it. Now go tackle your exam, and I know you're going to succeed at it. Thank you so much. You're going to do great, and I hope to see you in the Green Belt course. Thank you and talk to you all soon.